Okay, in this video, in preparation for looking at the Rankine cycle, I want to look at pumps. Okay, pumps, basically their job is to increase the pressure of a flowing liquid. They're going to be steady state, there's going to be one stream in, one stream out. They're usually well insulated, so Q is zero, kinetic and potential energy changes are usually not important. And so I end up with exactly the same set of equations as we had for the turbines. So mass in equals mass out, the work is the enthalpy in minus the enthalpy out, and the entropy generated is the entropy out minus the entropy in. Got here just a couple of pictures of a centrifugal pump, which is the most common kind of pumps that you think of when you think of like just flowing a fluid in a pipeline or something like that. A centrifugal pump is very common. The kind that are used, the pump jacks for oil industry, you see that look like the little horsey heads dotting the landscape of Oklahoma. Those are going to be primarily reciprocating pumps. So this is kind of our basic start with it. Now what happens is I need to analyze stuff, but they're not exactly the same as a turbine. Just because the equations are the same, I don't really end up with the same situation. First of all, the power is going to be negative, so the work is going to be into the system instead of out of the system. Also, these only operate with liquids. Now, if the water is, or if the liquid is a water, that's not a problem. I've got compressed liquid tables, and I can just look up values of the enthalpy. But if I have other substances, this isn't going to be available, this data. And so what we do is we take the first law for a steady flow system and combine it with that definition of entropy, which became what is usually called the TBS equation. And so for a reversible system, what I find is that for a flow situation, the work, the specific work, is the negative integral from the inlet to the outlet of the specific volume times the change in pressure. Okay, so far so good. This isn't useful for very often. However, for liquids, there's usually not a really significant change in the volume, so I can actually integrate that. Now, if you recall, that had a negative sign in the integral. So as a result, I end up with the pressure at the inlet minus the pressure at the exit times the volume is a good estimate for the work from the pump. Okay. Now be careful with your units here. If you're using cubic meters per kilogram for volume and pressure is in kilopascals, then your pressure or your work units will be in kilojoules per kilogram. So if you don't have a compressed liquid table and you have a compressed liquid, what are you going to use to estimate V? Turns out that the saturated liquid properties will be very good estimates for the any compressed liquid, really any compressed liquid, but match the temperature. Don't worry about the pressure, match the temperature. And if you do that, saturated liquid is very close to being a compressed liquid as far as data goes. Now, remember, I've made a couple of different assumptions here. So this isn't going to be a perfect answer, but it's going to get me out of a bind. So I have a little example here. I want to find the power required for a pump that's pushing 3 kilograms per second of water from a saturated liquid at 200 kilopascals to a pressure of 2.5 megapascals. So if I do this, I'm going to work this problem twice. First, I'm going to just do it straight from the tables. Because it's water, I have all the tables. So the inlet, I've been given saturated liquid at 200 kilopascals, so I can look that up, and at 200 kilopascals, I have VF, I have UF, HF, and SF, and I can just look these numbers up. When I go to look at the exit state, if I'm assuming that this is an ideal pump and they gave us no information otherwise, then what I'm going to do is I'm going to say that, well, ideally it's reversible and adiabatic, which means isentropic. So the entropy at the inlet will be the same as the entropy at the exit. They gave us the pressure, so I have pressure and entropy at the exit. And I can use those. So I found the data for 2.5 megapascals, and I look for the entropy value, and it's of course not in the table, so I interpolate. And if I interpolate, I find that the temperature is roughly 60, volume and enthalpy at the exit. And so if I'm going to calculate the power required to operate this pump, I just simply subtract those two values of H, multiply by the flow rate, and I get negative 15 kilowatts. Okay? Now that's pretty good, and if you have that data, that is definitely the way to go. But let's try doing it without the data. Let's pretend the compressed liquid table wasn't there. So I look up the properties for my inlet. In this particular case, saturated liquid, I have this data. If I knew the temperature and pressure, I'd go with the temperature and match that data. But I need volume. That's the only piece of information I need. So the specific volume is a small number. I'm going to multiply it by the pressure change, pressure in minus out. Multiply that by the flow rate. I've got kilograms, canceling here. Cubic meters times kilopascals is kilojoules, so kilojoules per second is a kilowatt, and I end up with the work as negative 7 kilowatts. Okay, now this should be vaguely alarming that I had negative 15 before, and now I have negative 7. Now most of the time, this is a rather extreme pressure change, so the larger my pressure change, the worse of an estimate this is going to be. But this, remember, is always an estimate. If I have a choice, don't do this. Okay, the other one's going to be better. Percentage-wise, this is like half the value of the other one, right? So that's terrible. But if I'm looking at it in terms of just raw numbers, I missed it by 8 kilowatts. Well, in the scheme of things, 8 kilowatts is going to be small compared to some of the other mistakes that I could have made in my estimation. So it's okay, it's just not great. I have one last little topic I want to address on pumps before we move on, and that is pump efficiencies. I'm not going to work an example on this one. We just did one on turbines. We'll do some in the future. But on pumps, remember that the work is going to be required. So the ideal is going to be smaller value than what actually is required. You always have to pay for more, right? It's always more expensive. So the actual value is the large number. To get this less than 1, I'm going to have reversible work over actual work. If I'm using the change in enthalpies, then it's the inlet is the fixed value, the ideal is the exit, or the exit is the ideal for the numerator and the actual for the denominator, corresponding to which work is on the top and bottom. So what is my ideal? Well, most pumps are going to be insulated as a good assumption, in which case Q is 0. If that's the case, then reversible plus adiabatic means that my ideal is isentropic, or the entropy at the inlet is the entropy at the exit. But some pumps are going to have cooling jackets. Q is not 0. I'm going to have to actually go through and redo my mass balance, or my energy balance there, and include the Q value. In that case, my ideal is going to be isothermal, and the temperature at the inlet is going to be the temperature at the exit. Okay? So you need to know how your pump is operating in order to know what your ideal is. So this gives you a refresher on pumps. Next, we're going to look at boilers.